look at another obviously very important topic, which is doping. And some of you are already familiar. So we'll start off with things that are familiar with you and then go on to more advanced concepts related to doping here. So this is a very simple picture of doping that you have seen, I think, even in your 12th standard, that you have a silicon atom which is bonded to another silicon atom in a lattice. These are the shared electrons that are there, right? These are the covalent bonds between two silicon. This is what we call as a bond model of the silicon lattice here. And you know that N-type doping means that you remove one silicon and replace it by a group 5 element here. So you do, for example, a typical group 5 element would be arsenic. Arsenic, as you know, has 5 electrons. All 4 of them are used up in bonding here. And it has one extra electron, which is sort of, we say, loosely bound to arsenic. And we say that at room temperature, there's enough energy available for this particular electron to become free. And therefore, it's available for conduction. It's not held to a particular arsenic atom. It's available for conduction. It's free, right? So that's the picture that we have. And therefore, by adding each one arsenic atom, you add one particular electron to your system here, which is available for conduction. So this particular electron is actually going into the conduction band. All right, so that's the picture that we have. Similarly, for p-type doping, the picture that we have is boron, that you take a silicon atom, replace it by group 3. So you replace it by boron. Boron has 3, so it has one less electron. So it captures it from another site, an electron here. Boron captures it, so it completes its outer shell and completes the bonding here, but leaves the site a vacant state here that you see. And that is our hole. Right, so this particular one is a hole, which is now available for conduction because an electron from here can jump into this particular hole, and therefore the hole can move around inside your lattice here. Right, so that's the picture that I'm sure all of you are familiar with, N-type and P-type doping here. All right, as I said, we want to now, this is a bond model, which is telling you what is happening. It's a simplistic picture. Let's look at it in terms of band, energy band diagram. What happens when I introduce a N-type donor? And so the picture that the background concept that you require is, you will see in a minute, is that of a hydrogen atom, which again you are familiar with. Hydrogen atom, as you know, is an electron held to a nucleus through an attractive force. And quantum mechanics allows us to predict the various properties of this hydrogen atom. One of them is that it has, you know, that there are different energy states that are possible, 1s, 2s, 2p, and all of that. Because it has one electron, so normally, in a hydrogen atom, the one electron sits in the lowest energy state here, and we show it here, right? And this is the nucleus, and this is the Coulombic potential, right? Coulombic potential energy here. And you may also remember that it takes about 13.6 eV of energy to remove an electron from the 1s state to the vacuum outside here, okay? So this is the vacuum level with which we are familiar now. This is the vacuum level E0. And the 1s state is 13.6 eV below that. Okay, so that's the picture. I'm just reminding you of what hydrogen atom is, what the prediction of quantum mechanics is with respect to energy and the different states that are there. Now, what we'll see is that this group 5 element that you've added, arsenic in silicon, can be modeled like a hydrogen atom. I'm not going to go into a rigorous way of showing it, but you can imagine now what is happening. And there's an energy here. The energy, we can, through solution of Schrodinger's equation, we can calculate this particular energy here, which depends on the mass of the electron, depends on charge, of course, and depends on, h square and E0 square, which are physical constants here. So it depends on that. And if we plug in all the values here, we get a value which agrees very well with the experiments here. Okay, so that's the energy. You can say that's the binding energy that you have for this electron. All right. The picture that you have now of a donor that I just sketched is that this donor atom that you have here, right? It has one extra electron that you see over here, right? And the donor atom, you can think of it as positively charged, obviously, and the electron is a negatively charged here. So you can imagine that I can think of this interaction between this positively charged atom and this particular electron. I can imagine it like a hydrogen atom. I can model it like a hydrogen atom. This is an electron which actually belongs to the arsenic here, and arsenic is positively charged. and this is negatively charged. So you can imagine that this is like a hydrogen atom. Except what? This hydrogen atom is not in a vacuum. In between an electron and a nucleus is vacuum. What do you have in between an electron and an arsenic? Not really other electrons, but you have the whole lattice which is there. What we will show you, what I can show you through, some calculations, that this electron, see, typically if you look at this particular electron in a hydrogen atom, how close is it to the nucleus? What is the length scale? One can calculate average distance is about an angstrom. 1 angstrom roughly is a number that you can carry in your mind here. 1 angstrom away. Now, what I can show you is later, through these equations, that this electron would be away from this particular arsenic much larger than 1 angstrom here. It may be 100 angstrom or even more. So when it is much larger, you see the radius that you draw here is much larger. So what you would find is that around it is a lot of silicon atoms. So imagine this particular electron as very far here, on an average, very far from the arsenic here. So this electron here is attached to arsenic, but in between, what do you have? You have all the silicon lattice which is there. Okay, that's one thing to keep in mind. The other thing is, note that here, when I ionize my hydrogen atom, where is it going? To vacuum. When I ionize this particular one, when I remove it from its influence, where is it going? To the conduction band. It becomes free. It goes to the conduction band here. So can you see that now this is the picture that I have here, right? This is what we are saying is we are modeling this electron and donor ion interaction as a hydrogen atom. Okay. And what we are saying is now the donor atom, note that what happened in a hydrogen, the 1s electron appeared below E naught, below vacuum level by 13.6 eV. Now what we are saying is this particular electron, when you ionize, it goes to the silicon lattice, right? It goes to the conduction band. So where will the, when you free it, right? When you free this particular electron from the influence of arsenic, then it will go to the conduction band. But when you don't free it, where is it? When you don't free it, it will be something like a 1s state. Where will it be? Below EC. And that's what we denoted by a donor level. We say that there is a donor level here, and that's where the electron is normally sitting. But if you free it, it goes to the conduction band, right? Look at the analogy between this donor atom. The analogy that we have is between these two here. Normally, hydrogen atom, this is where the electron is. When you free it, it goes to the vacuum level outside. Now what we are saying is this can be modeled like a hydrogen atom. When you free it, so normally it is at some energy, ED, donor level. Okay, the electron belongs to arsenic and it is in this particular level here. When you free it, where does it go? It goes to the conduction band. It doesn't go to the vacuum. We are not talking about the vacuum. We are not talking about ionizing it outside the lattice. If we are talking about ionizing it, taking this electron outside the lattice, then I have to worry about vacuum level. I'm only talking about freeing it from the influence of arsenic and taking it to the conduction band here. So that's the picture. What happens when you add donors? It introduces levels like this here that you see here. And that's where my electrons normally belong. This extra electron that you see here, it normally belongs here in these levels here. And if you give it enough energy, this electron will go here and it becomes free. So that's the picture that we have of what happens when you add a donor atom to your silicon here. It introduces these levels here, donor level here. Okay. This energy is important. Now, what we can do is note that this energy, if we calculate, remember this expression here? This is the expression for, so we are modeling it like a hydrogen atom. This is the expression for the ionization energy. But note the difference. The difference is, should be put on mute. The difference is, if you note that the difference is that, that this electron is actually moving in a not 1 angstrom radii, but moving in a much larger one. So what we do is all these silicon atoms are intervening in between, and therefore you can imagine that the attraction between the electron and this arsenic will be affected by the dielectric constant of the medium, right? Force of attraction between two, a negative charge and a positive charge, is E naught and ER. Dielectric constant comes into picture, right? So what we are saying is this electron is moving in a much larger radii, and in between all these silicon atoms are there. And when you have all these silicon atoms in between a negative charge and a positive charge, the dielectric constant of silicon comes into picture. So this energy that you see here, E, instead of vacuum E naught square, you start getting a dielectric constant also, ER square here. So that's the change that happens to energy. So one change is ER square here. The other thing is, we said that electron inside a lattice, you can model it in terms of effective masses, right? So instead of the rest mass Me that you see here, you start getting effective mass of an electron here. So you start putting effective mass here. So if you do that and you calculate the energy, remember this energy was how much? 13.6. The dielectric constant of silicon is 11.7. 11.7. So you can imagine now, if you take dielectric constant 11.7 and square of that, and you divide 13.6 by that, how much, where will it go? You're roughly dividing it by a factor of 120 or so, right? So if you divide it by a factor of 120, you're going towards 100 milli, right? 100 milli electron volt. And plus mu is smaller than this mass here. So you're going into energies which are few tens of milli electron volt. That's where you're ending up. The hydrogen atom that you picture here is predicting that the energies will be few tens of milli electron volt. Okay, you can just work out the numbers. 13.6 divided by ER square plus the effective mass of an electron is smaller. And if you add, put in all those factors, the energies will turn out to be that much here. Okay, so very small binding energy. And that's why you can easily promote an electron from here to here, and the donor ionizes and releases this electron to the conduction band here. Okay, so that's the picture that we have in terms of bands. That what is happening when you add a donor atom, you introduce a level here. Each donor atom, as you may imagine, will introduce its own level at a certain point here. Okay, it depends on, these equations are to some extent simplistic. It does depend on the nature of the donor atom also. So ED will vary a little bit on the nature of the atom also. And so this is what happens here. You introduce these levels here. Normally the extra electron is sitting here, and with enough energy, it can go to EC and then become available for conduction. One more thing you notice, I've drawn EC as continuous and ED as broken. Why? EC continuous means what? If you see here, it means, remember I was saying that you have a state which extends all over the lattice. It's a delocalized state. Normally electrons in conduction band are delocalized over the entire lattice here. Okay, and while here, once it is there, it's localized to this particular only arsenic atom, right? And therefore one arsenic atom will introduce one level here. Another arsenic atom somewhere else will introduce another level there. Two arsenic atoms, remember, on an average, the concentration of donors that we add is small. So the separation between two arsenic atoms will be very large, so that there's very little interaction between them. Okay, so they are all localized states. Once an electron is in arsenic, it's a localized state here. That's why the broken line shows localized here. Another picture, here we have shown that these are at equal intervals, right? Remember what this axis is? Vertical axis is energy, horizontal axis is spatial x. So now these donor, the levels are not going to be at equal intervals. If I have one donor here, I will have a level. Then after some time, I may have another level here. So it's going to be non-uniform, right? The donors that you add are non-uniformly distributed. So it's not that, there's a donor atom at every 100 nanometer or something like that. It's not so neat like this here. One you may have here, another you may have here, then one other very close, and, randomly distributed. The point is not that they're evenly spaced. The point is that they have a certain energy level, which is well-defined, ED, each donor. Okay, well-defined energy here. All right. So at t equal to 0, let's imagine at t equal to 0. Obviously, then I don't have any energy. All my donor atoms, the extra electron that is there, is all occupying this particular level here at t equal to 0. Okay. And at t equal to 300 K, let's say, or any other non-zero temperature, the usual assumption that we, many times we make is that there is enough energy available at room temperature so that all these electrons that are there, they just, they go to the conduction band. All my donors get ionized here. Now I'm going to look at this particular phenomena in more detail. Do all of them get ionized? And what are the conditions under which they will get ionized here? Okay. And the answers are not so simplistic that you add certain number of donors and all of them ionize here. Okay. Now, so many times we make, and we later on in the course we'll do that. That number of electrons is equal to number of donor atoms. But remember that this condition will only be true under certain conditions, and that's what we want to know. Under what conditions can we say N0 is equal to Nd? All right. So let me give you the values here. Look at that here. If you add arsenic, which we will take as a typical case, the arsenic introduces a donor level which is 54 milli-electron volts below EC. Phosphorus is about 44, antimony about 39, so they're reasonably close to each other. But we'll take this particular number as a typical case here. If you add an N-type donor, arsenic, to silicon, it will introduce a donor level 54 milli-electron volt below the conduction band. All right. How much? So this is the level now. Keep that in mind. 54 milli-electron volt below the conduction band. How much energy do I have at room temperature? Typical value that you should carry in your mind. KT, which is how much? 26 milli-electron volt. Is this true then? This donor lies 54 milli-electron volt. Average energy that I have available is about 26 milli-electron volt. Is it true that all of them will get ionized? But we do make that assumption, right? N0 equal to Nd, we keep on doing it. Look at the energy values here. 54 versus 26. Is it true that all of them will get ionized? Huh? So, but it does happen that most of the donor atoms do ionize here. Why is that? Okay, to understand that, let me put this picture here. Okay, so let's look at in a little bit more detail here. So the issue is, will they ionize or not? Will they not ionize, right? How do we answer it? We can answer it through, let's say, Fermi-Dirac probability distribution function. We're talking about equilibrium, right? Equilibrium, Fermi-Dirac tells us what is the probability of occupation of an energy level. That should help us answer the question whether my electron would like to stay in ED or would it like to go to EC. So I should look at Fermi-Dirac function here. All right. So let's say EF is here. Let's take a typical number, Nd equal to 10 to the power 16. And obviously, if you have Nd equal to 10 to the power 16, your N0 is going to be either equal to Nd or less, right? Because normally, if you don't put any donor atoms, how many electrons are there? The intrinsic carrier concentration, which is how much? 10 to the power 10. For silicon, that's the number carry in your mind, 10 to the power 10. So now that I've added donor atoms, the best case scenario is all the donor atoms get ionized, and then I will get 10 to the power 16. Otherwise, I will get less than that. So this is fine. N0 will be less than 10 to the power 16. Now I know this, N0 equal to Nc exponent minus Ec minus Ef by Kt. So gradually what I would want you to do is, when I say will all the donor atoms ionize, rather than saying, well, they'll all ionize, they will not ionize, start using equations. All the answers that you want can all be obtained from the equations that we already have in our toolbox. All the equations, in fact, I gave you right up front, right? Fermi-Dirac function you have, N equal to Nc you have Poisson's equation, continuity equation, all of these equations you have, all the questions can be answered through that, okay? And so we'll see how to do that, okay? So N0 is Nc exponent Ec minus Ef by Kt. What is that equation telling us? See, to answer this, so my strategy is as follows. We want to know whether all my donors are ionized or not. Okay. So what I'm looking for is, what is the probability of occupation of EC versus what is the probability of occupation of ED? I want to do that. Look at that, right? Probability of occupation should help me answer that, right? They should help me answer that. But to use this, I need EF, right? I need EF. So how do I get EF? Well, so that's what I'm trying to do. Nd equal to 10 to the power 16. So I'm saying N0 is at the most 10 to the power 16 here. But then if I look at N0 is Nc exponent Ec minus Ef by Kt. So this is what relates the EF to N0 here. All right. So what does this equation tells us? This equation tells us the position of Ec minus Ef. Right? It tells us Ec minus Ef in terms of N0. So if my N0 is less than 10 to the power 16, it says Ec minus Ef must be greater than 0.206. All I have to do is just put NC value and N0 value here, and then we'll get the value. We are talking of everything right now at room temperature. So T also we know. So it tells us EC minus EF is greater than 0.206. So it says EF is either at 0.206 or lower. Okay. So what we can do is the following. We can, there are various ways of doing it. We can assume that all the donors are ionized. Okay. Start with the assumption all the donors are ionized. Okay. If that is true, N0 is 10 power 16. I know the value of EF. Correct. Now I know with that assumption where is the value of EF. Then I go ahead and put it here, and I can check whether my assumptions are true or not. Okay. So now that I get a value of EF, I put it here, and I calculate what is FEC. Okay. Note that FEC would be what? EC minus EF. EC minus EF, you know. So what is the probability that a state at energy EC is occupied? Well, it tells me this is the probability. Then I ask, what is the probability that a state at ED is occupied? FED turns out to be 2.84, 10 power minus 3. How do I find this out? Well, what you do is you put here ED. So ED minus EF. But I don't know ED minus EF, but I know ED, difference between EC and ED. So you can get what is ED minus EF also. Okay. So you find out probability of occupation of energy state ED is so much here. Let me take the ratio. FED by FEC is 8. Okay. So what can you conclude from here? Probability that ED is occupied as compared to probability that EC is occupied is 8. Then what is it telling us? What did we start with? We started by assuming all the donors are ionized. And then we come to this conclusion. Is it contradictory? Yes? So all are not ionized? Okay. Okay, so this is the picture that we have. Let me ask you this here.
How can you share it like this is only a probability ratio?
You're right. This will tell you. Okay. Suppose I have a glass of water. Right? I have a glass of water. I leave it outside. I leave it outside. Right? What will happen? Leave it out. The sun is not very bright these days. But suppose I do leave it out. What will happen? Right? This is what will happen. Why are the water molecules going to a higher energy state? They're going to a higher energy state, you agree? They're going to a higher energy state. Why is it empty? Why is it empty? Huh? Entropy comes into picture. Yes, you know that. But so you're saying that just because, so here, if I think of a water molecule's energy is lower in the water and higher in the vapor state. You agree with that? But still you're saying that it's all empty. And in fact, if I leave it for a long enough time, what will happen? There will be nothing available here. Is it relevant to what we are talking about? That I have, this is a higher energy state, but if I leave it for a long enough time, all of them will ionize. Is that relevant? Now, suppose I ask you this also. Suppose I took this glass and put it in a small jar, small container. Will it still, you think, lose all this water? Huh? Will it lose all this water? What is happening here? Entropy, you're saying, yes, what else? I mean, related to entropy. So where am I wrong then? I'm saying FED by FEC is 8. And so what you're saying is, well, my glass is going to empty. Similarly, all my donor atoms will empty. Will similar. What else should I take into account? You are right. You were raising this issue of probability is not the only thing, right? What else should I take into account? Something which is very important, which is missing. No, time we have said equilibrium. Equilibrium means we have left it for long enough time. What else is missing? Number of states. This is just giving you probability. How many electrons are in ED will be how much? The probability multiplied by number of states in ED. How many electrons are there in EC will be probability that EC is occupied multiplied by number of states. This is not fair just to take into account here. This is not fair. So what I should do is the following. Number in ED will be equal to ND multiplied by FED. And number in EC will be equal to NC is the effective density of states here multiplied by FEC. If I do this now, and what does my number turn out to be? 2.8 into 10 power minus 3. right? 2.8 into 10 power minus 3, which means that there is very little left in the donor here. Almost all of them are here. Now, what does covering? So you can see that in this case, the number of states outside is like infinite, right? You know, you've left a glass out in the open. The number of possible states, entropy is related to number of possible states. So the number of possible states outside is infinite, and therefore it will all empty. But then when I cover it here, number of states, number of possible is less. And you know the concept of relative humidity and all that will increase, and all the glass will not empty. So you are saying that this number of states is important, and here also the issue of whether all the donor atoms ionize or not is related not just to ED, but is related to what is the number of states here and what is the number of states here. ND and NC tell you how many states are there at ND and how many states are there at NC. Right? So whether a donor atom ionizes or not, it depends on ED, where ED is with respect to EC, but it depends crucially on this ratio here. Okay. Now note that I put 10 to the power 16, right? 10 to the power 16, and I find that all of them are ionized. But suppose instead of 10 to the power 16, I put 10 to the power 19. I increase ND by 3 orders of magnitude. What will happen now? 3 orders of magnitude if you introduce, so you get multiplied by 10 to the power 3, and what do you find now? They are not ionized. So a very wrong, sometimes one carries a very wrong picture by saying all that matters is the difference between EC and ED, the energy. If the energies are very small, it will get ionized. Well, energy here is not too small, 54 milli-electron volt. At 10 to the power 16, everything gets ionized. But then if I add 10 to the power 19 donor atoms, I mean, only a fraction will get ionized here. So whether a donor atom ionizes or not depends on the energy, of course, and depends on what is the density of states here. NC is very important, and how many donor atoms I've added. This ratio is important here. Okay. All right. So let's then. This is sort of a simple view. Let's now work out some numbers here. So what we want is what is the condition? We know now that whether a donor atom is ionized or not depends on what? Depends on the separation EC minus ED, and depends on how many donor atoms I've added and how many density of states are there. All these factors, you can see it here. ND, NC, ED. These are the factors that determine whether a donor atom is ionized or not. And now we would like to determine a simple expression, which will tell us that suppose I add 10 to the power 16 or 10 to the power 17. Will all the donor atoms be ionized or not ionized? For any system. Okay, so we want an inequality which will help us get that number here. Okay. Okay. All right. Okay, so before we do that, one more sort of digression, but important here. All right, so we have been saying that the probability of occupation of a state is given as 1 plus exponent E minus EF by KT. Okay. However, the probability that the donor level is occupied by an electron, we often, you will find if you read books, that it's written as 1 plus half exponent ED minus EF by KT. It's not written as exponent ED. If you directly start from here, you would obtain ED here. ED minus EF, and this half factor appears to be out of blue, right? One cannot get that. Let me explain where this half factor is coming from. If you take this Fermi-Dirac probability distribution function here, and you take Fe divided by 1 minus Fe, okay? Just from here, Fe divided by 1 minus Fe is exponent EF minus E by KT. Now the way, what does Fe denotes? Fe denotes the probability of occupation of a state. 1 minus Fe denotes the probability that a state is not occupied. Okay, so it's the ratio of these two. Now, the way it is derived, it's assumed that there is one state available, and you're looking at whether the state is occupied or not occupied. But here, there's a little bit of a issue here. Let me generalize this by saying is the following, slightly different. The probability of occupation of a state divided by probability of not occupation of a state is this factor here. But then what I've introduced is another factor which says number of ways in which you can fill a state and number of ways in which you can empty that state. You can imagine that probability will get affected by it. If there are more ways of filling a state than emptying it, then Fe will, then the probability will change here. Okay. Let me explain what is happening here. Take this donor atom here. how many ways of filling a state a donor atom is there? All right, let's see. Okay, so it's note that here. So this is an empty state here. In how many ways can I fill? I can fill it with a spin down, or I can fill it with a spin up. There are two distinct ways in which I can fill it. How many ways can I empty? Well, let's say there. How many ways can I empty? If I take this donor atom, only one way. I can just take it out. It's not that I have two options available. If I go to any particular donor atom, either it will have a spin up or a spin down electron. I have only one option of taking it out. While filling it, I have two options. I have two different ways in which I can fill it, but only one way in which I can take it out. This is what is adding to this part here. See, when Fermi-Dirac was derived, this distribution is derived, these differences have not been taken into account. There are two distinct ways in which you can fill it, and therefore filling becomes more probable. There are two ways in which you can fill, and only one way you can take it out. All right. So we have to add that here. Number of ways in which you can fill is 2, and number of ways in which you can empty is 1. So this then becomes FED by 1 minus FED becomes this factor multiplied by 2. And then therefore you can see here, it goes back and says FED equal to 1 plus half. Okay, taking into account these are called degeneracies. The fact that I have two ways in which you can fill and one way in which you can empty. So you have to look into these factors, and then they result in a more realistic expression for probability of occupation of a donor state, which is FED is equal to 1 plus half exponent ED minus EF by KT. Okay. All right. So we'll use this and then look at donor ionization in a little bit more with a little bit more analytical expressions here. Okay. All right. So this is the probability of occupation of a donor atom. The probability that my donor atom is ionized, Nd plus, will be equal to Nd 1 minus FED. 1 minus FED is what? The probability that is not occupied by an electron. Okay. So we do that. 1 minus FED. So it can be written as Nd 1 divided by 1 plus 2 exponent EF minus ED by KT. Let's define this quantity here. Okay. So Nd plus we have. So what is Nd minus Nd plus divided by Nd? It tells us the fraction of donor atoms which are not ionized. And what do we want this? We want this factor to be much smaller than 1. Right? So that, when we've added donor atoms, we want them to ionize. Okay. So we want this factor to be much smaller than 1. So Nd minus Nd plus divided by Nd, straight from here, I can get this expression here. Okay. We want this to be much smaller than 1. Much smaller than 1 means what? Obviously, this factor must be much smaller than 1. Otherwise, I can't get it. Okay. So you can see here that zeta here becomes approximately equal to numerator only. So 2 exponent EF minus ED by KT. All right. So this is the condition that must be, if I want most of my donor atoms to be ionized, then Nd minus Nd plus by Nd is equal to so much. All right. So let's start from here. Now Nd minus Nd plus by Nd equal to 2. I write this as EF minus EC plus EC minus ED by KT. Okay. You can see why I'm doing it. EF minus EC. What does this remind you? Anytime I see EF minus EC by KT? Which equation reminds you? This one. N0 equal to NC exponent minus EC minus EF by KT. Right. So I'm going to take EF out, EF minus EC from here, and express it as N0 by NC here. So I can get Nd minus Nd plus by Nd equal to 2 N0 by NC exponent EC minus ED by KT. EC minus ED is what? A fixed quantity. Every donor has a fixed level. So this is fixed now for me. Okay. This is fixed for me. All right. Now we are saying most of the donor atoms are ionized. Right. We want this term to be much smaller than 1. Under that condition, what will N0 be? N0 will be approximately Nd. Most of the donor atoms you want it to be ionized. So N0 is approximately equal to Nd. So can I say that the fraction of donors which are not ionized is equal to 2 Nd by Nc exponent EC minus Ed by KT. And we want this to be at least less than 0.1. The number of donors which are not ionized should be less than 10% at least. Well, you can put here 1% also. This is sort of arbitrary, but at least less than 10% here. So now we are getting a condition. We are getting a condition that must be obeyed for at least more than 90% donor ionization. And this is the condition that you must satisfy. Your ND has to be, it is just rearrangement here. ND has to be less than or equal to NC, density of states, divided by 20, exponent minus EC minus ED by KT. That's the relationship you must obey. If your semiconductor obeys this particular relationship, you can say, well, almost all my donor atoms are ionized. And therefore, number of electrons is equal to, approximately equal to ND. If this equation is not satisfied, then you have to worry. Significant fraction is not ionized, and then you have to go ahead and do some more calculation to figure out how many are ionized and how many are non-ionized here. But this is the essential condition here. Under this condition only, you can assume that all the donor atoms are ionized here. Okay, so let's look at this condition then. So note that it has two terms here, NC, which is a constant, EC minus ED is a constant, but is temperature dependent. Okay. In some sense, this should, an analogy is like solubility limit, right? You add certain amount of sugar, it will dissolve, right? If you add beyond that, it will not dissolve. It's the same thing. You add certain number of donor atoms, it will ionize. Beyond a certain amount, it will not ionize. Less and less will ionize, right? And how much is the solubility limit? Remember, it depends on the temperature also. If you raise the temperature, you can dissolve more salt or sugar, right? If you raise the temperature, you can add more donor atoms. Okay, so it's a similar kind of a concept here. So let's put in some numbers here. NC 2.8 into 10 power 19 is the density of states. EC minus ED, as we said, for silicon, we'll take this number, 54 milli-electron volt. And so if we plug in the numbers, we find for ND less than or equal to 1.7 into 10 power 17. That's the number at room temperature, at T equal to 300 Kelvin. This is the number below which, if you have added a number of dopant atoms which is less than about 10 power 17 or equal, you're okay. All of them will ionize. Otherwise, a significant fraction will not ionize, and then you have to, as I said, do some more accurate calculations to figure out how many are ionized and how many are not ionized. Okay. Now, as I said, this depends on the temperature also. So, for example, in this case, we said, let's fix T equal to 300 K and find out how many donor atoms I can add and still have almost 90% ionization. So this expression gives us. Another thing that I can say is, suppose I add a certain number of donor atoms. What is the lowest temperature I can go and still get 90% ionization, right? So for example, if I add ND equal to 10 to the power 16, obviously it obeys this limit at room temperature. But how low can I go in T and still it obeys this particular limit? Okay, so I can ask that question, and you can simply rearrange this equation and get this T, that as long as for a particular donor concentration, as long as T is greater than a certain value, you have almost 90% ionization. Okay, so for example, if I put 10 to the power 17, what will be my limit? What will be T? See, this limit is at room temperature. So T is going to be room temperature. If you go below room temperature, you'll start getting, a donor neutralization here. So for ND equal to 10 power 16, suppose we had asked determine T at which donor neutralization begins to occur. Is just the same thing. Neutralization means, some of them are not ionized anymore. Okay, begins to occur. What will I get? So I know EC minus ED is 54 milli-electron volt. I know NC 2.8 into 10 power 19. And ND is 10 power 16, so I can find out the value is 126 Kelvin. So if you've added 10 to the power 16 donor atoms, you can go down to almost 100 degree Kelvin, close to 100 degree Kelvin, and almost 90% would be ionized. If you go below that, well, then less and less will be ionized. Okay, and less and less will be ionized, which means more and more will be neutral. Donor atoms will be neutral here. Okay. All right, so let's, as I said, we'll have one problem. So let's work out this problem here. Any equations that you want? I know it's not in half an hour time. You can't remember and absorb all the equations. So I'll give you the equations that you want. So the idea is as follows. I have two semiconductors, A and B. All right, in one semiconductor, EC minus ED is 6 milli-electron volt. the donor level is very close to the conduction band. And in another case, the donor level is 40 milli-electron volt away from the conduction band. Right? Two different semiconductors. In both of them, I add the same amount of donor concentration. Both of them the same amount of donor concentration. In which case will greater ionization of donors takes place? All right. I'm sure you don't know where to start, right? In which case will greater ionization of donors takes place? Two different semiconductors. EC minus ED is 6 milli-electron volt. Donor level is very close to the conduction band. EC minus ED is 40 milli-electron volt. Do you need any other equation, or you can answer it right away? One is 6 milli-electron volt, the other is 40. Can you answer on this basis? No? That's the important point. First thing you should say, I can't answer. See, if you don't know enough about this, you will say, okay, 6 milli-electron volt is very close to conduction band, it will ionize. That's not true, right? It depends not only on the ED, but it depends on NC. So you should ask, the thing was, give me NC values also. All right, so I'll give you NC values here. NCA is 4 times 17. NCB is 4 times 19. Can you readily answer by looking at these numbers? Okay, suppose I had made it simple. Suppose NCA had been 4 times 19 and NCB was 4 times 17. Let's have a simpler one. NCA was 4 times 19 and NCB was 4 times 17. What promotes donor ionization? One is EC minus ED should be as small as possible. The other one is what? I should have a lot of states in the conduction band, right? So if I had said 4 times 19 here, the case is sealed. I have, ED is close to conduction band, and I have 4 times 19 more states also in the conduction band. There's no issue. A will be more ionized. But now this is a complication. ED is closer to EC, but then number of states is less. And ED is further away, but number of states is large. Now you can't answer, you need equations, right? And which equation do you use? Well, use this equation. Can you use this equation to answer in which case? That's the key equation that you should remember. It's not too hard to remember. You know that EC matters and EC minus ED matters, right? NC matters and EC minus ED. Whenever you have an energy, you will always have e to the power minus EC minus ED by KT. All right, you will always have an exponential divided by KT. And this is NC by 20. So it's not hard to remember. It's not hard to remember. Okay, is the answer out? B, right? So we look at this NC by, so we look at this ratio here, ND divided by NC by 20 exponent EC minus ED by KT. So this term here, this is the important term. This term turns out to be for A, 1.6 into 10 power 16. For B, it turns out to be 4.3 into 10 power 17. And therefore, the chances of greater donor ionization will be in B. Now, the reason why this particular example has been given is that if one just looks at 40 and 6, one would expect that 6 would be, the donor is closer to the conduction band and therefore is easier here. And the example is important also for the following reason, that if you look at gallium arsenide is another very important material. NC for gallium arsenide is 4.7 into 10 power 17. NC for gallium arsenide. And the typical donor in gallium arsenide is at 6 milli-electron volt. Okay, so this is like gallium arsenide and this one is like silicon. So you take 10 to the power 17 donor atoms, you put it in silicon, 10 to the power 17, almost all of them will get ionized in silicon, while in gallium arsenide, a significant fraction will not get ionized. Okay, even though EC minus ED is 6 milli-electron volt in this particular case here. So these are important examples because in one case, this is like gallium arsenide here. This example is like gallium arsenide and this one is like silicon here. Any issues with the number? Numbers are okay? All right. Okay, so we have 2 minutes All right. So this is the limit that we saw, that as long as you dope your semiconductor and it obeys this particular limit at room temperature, almost all are ionized. But if you lower the temperature, what would happen is, well, most they will remain ionized, but after a while you will start violating this limit. Right? At room temperature, you may find that Nd is the right hand side and the left hand side. Left hand side is less than the right hand side by, let's say, a factor of 10 or 100. But then as you lower the temperature, what happens is the right hand side starts dropping. Right hand side starts dropping, and eventually what will happen is you'll start violating this. What does it mean? That now all the donors are not ionized. Right? And so what we can do is we can find out, using an expression like this here, what can, and maybe you'll do it as part of the homework assignment here. So for example, in this case, using the equations that I've given, you can determine Nd is 10 to the power 15, 10 to the power 16, Ed is 54 milli electron volt, and I'm plotting the fraction of donors which are ionized. Can you see that? N0 is what? Nd plus. N0 is Nd plus, so Nd plus divided by Nd as a function of temperature. See what happens? 10 to the power 16, room temperature, all are ionized, they remain ionized. Then as you keep on lowering, well, starts dropping and eventually becomes very, very small here. Now, if you want to look at this particular region in more detail, then what you should do is you should plot it against log scale. Then you see clearly here. So in a log scale, this is what happens here. N0 by Nd, and log scale, because there is you can see a 1 over T, so we plot it, it's more convenient to plot it as some 1000 divided by T, as 1 over T here. And you can see what happens here. N0 remains constant and then starts dropping. How does it drop? It drops exponentially here. And again, using the equations that you have, you can derive and show this, that in this region here, at low temperatures where it is dropping rapidly, N0 is square root NC Nd by 2 exponent EC minus Ed by 2 kT. Okay.